Physics is quite literally the blueprint of the universe. It's like the hidden instruction manual for reality itself. Today, we're going to unpack exactly how we decode that manual, starting from how we measure the absolute tiniest fragments of matter, all the way up to how we understand the complex motion of objects moving through our world. Here's our roadmap for today. We'll start with physics in our world, then look at tools of precision and unpack precision, accuracy, and errors. After that, we'll tackle significant figures, jump into the study of motion, and wrap up with distance, displacement, and speed. Let's get right to it. Okay, let's dive into Section 1, Physics in Our World, the Foundation of Technology. Think about this for a second. On one end of the spectrum, you've got microscopic robots designed to literally navigate the human bloodstream, fighting cancer at a cellular level. And on the other end, a massive space shuttle launching into orbit, carried by millions of pounds of thrust. The scale is completely opposite, yet physics is what bridges that massive gap. The fluid dynamics governing blood flow and the thermodynamics of rocket fuel actually rely on the exact same universal rules. How cool is that? There's a quote from our source material that really hits the nail on the head. Physics is the most fundamental of all the sciences. The laws and principles of physics help us to understand nature. But, here's the catch. To truly understand nature and build these incredible technologies, we can't just sit back and observe. We have to measure. In our human senses alone, they are wildly insufficient for the level of accuracy we need. Try eyeballing a fraction of a millimeter with your bare eyes. It just doesn't work. Moving right along to Section 2, Tools of Precision, Capturing the Microscopic. Because human estimation is inherently messy, we rely on some truly ingenious mechanical devices. Enter the micrometer screw gauge. Now, you might be familiar with a basic ruler or maybe even a set of vernier calipers, but this tool takes us a massive step further. It's specifically designed to measure tiny fractions of a millimeter. It is absolutely perfect for finding the exact thickness of a single wire or a really small metal bearing. Using this thing is basically an exercise in pure physical logic. First, you note the pitch and check for any zero error, meaning does it read exactly zero when it's closed. Next, you carefully place your tiny object between the spindle and the anvil. Then you turn the thimble. But the real genius here is the ratchet at the end. You turn that ratchet until it clicks. That click is absolutely crucial. It stops you from exerting too much pressure and crushing the object, which would completely ruin your measurement. Finally, you combine the reading on the main scale with the circular scale to get your highly precise number. All right, Section 3, Precision, Accuracy, and Errors, Order out of Chaos. Here is a truth bomb for you. Every measurement, no matter how careful you are, contains some doubt. That doubt is known as error, and it comes in two primary flavors. On one side, we have systematic errors. These are essentially flaws in the instrument itself, or your setup, and they skew your data in one consistent direction, kind of like a bathroom scale that always reads 2 pounds too heavy. On the other side, we have random errors. These are totally unpredictable. They're the tiny fluctuations in temperature, humidity, or even a human reaction time that make multiple readings bounce around slightly. You fix systematic errors by calibrating your gear, and you fix random errors by taking an average of a bunch of readings. Now, what's really interesting here is how we use the words precision and accuracy. We often treat them as synonyms in daily life, but in physics, they are entirely different things. Picture a dartboard. If your darts are grouped incredibly tightly together, but they miss the bullseye completely, that is high precision. The results are highly consistent and repeatable. But because they miss the mark entirely, they are highly inaccurate. In an experiment, a result like this usually points straight back to one of those systematic errors we just talked about. Section 4, Significant Figures, the Rules of Scientific Honesty. When you're dealing with these highly precise instruments, you often end up with a messy, super long string of decimal points. Significant figures help us round these off so we don't falsely claim more precision than our tool actually gave us. The rules are pretty straightforward. Under 5, drop it. 5 or up, bump the previous digit up. It's not like rounding up your grade on a test to make yourself look better. No, these are the strict guardrails that keep scientists completely honest about the exact level of uncertainty in their data. Let's move to and see how this builds in Section 5, the study of motion, entering kinematics. So the specific branch of physics we are looking at here is called kinematics. And the defining characteristic of kinematics is that it's the study of motion without considering its causes. We literally do not care about the gravity, the friction, or the massive push that set an object in motion in the first place. We are purely focused on the mechanics of the movement itself, the velocity, the acceleration, the exact path it takes. It is pure, unadulterated motion. All the motion in the universe basically breaks down into 3 main categories. First, we have translatory motion, which is an object changing its position as a whole, whether that's moving in a straight line or curving around a track. Then we have rotatory motion, which is an object spinning on a fixed axis, like a helicopter rotor or a spinning top. And finally, there's vibratory motion. That's the back and forth, to and fro movement around a central point. Think of a swinging pendulum or a plucked guitar string.
Which brings us to Section 6. Distance, displacement, and speed, navigating reality.
To navigate our reality properly, physics actually requires us to divide the world into two types of quantities, scalars and vectors. Scalar quantities are the simple ones. They only have a magnitude, which is really just a fancy word for a size or amount. Distance and speed are scalars. You travel 50 miles, or you go 60 miles per hour. Vector quantities, on the other hand, demand a direction. It's not just magnitude, it's magnitude and direction. Displacement and velocity are vectors. So it's not just moving 50 miles, it's being displaced 50 miles straight north.
Let's put this into perspective. Imagine you're driving from Faisal Masjid to the Blue area in Islamabad. The twisted, winding path of the actual roads you have to navigate, that is your scalar distance. But a perfectly straight, direct arrow from start to finish, totally ignoring all the buildings and roads in the way, that directed change in position is your displacement. You can travel a massive distance, but if you end up exactly where you started, your total displacement is a perfect mathematical zero.
So I want to wrap up this explainer by leaving you with a bit of a mind-bending question based on everything we've just covered. Is anything in the universe truly at rest? Think about a park bench on a quiet day. Relative to the ground beneath it, it has zero speed, zero displacement. It is perfectly still. But remember kinematics? If we shift our observer, everything changes. That bench is attached to the Earth, which is spinning on its axis at over 1,000 miles an hour. It's hurtling around the sun at tens of thousands of miles an hour. And our entire solar system is moving through the Milky Way galaxy. So the next time you sit perfectly still, remember, thanks to the brilliant instruction manual of physics, you are actually part of a massive, multi-layered system of continuous motion. Thank you so much for joining me on this explainer, and keep questioning the reality around you.